This conference will now be recorded.
Good afternoon, all. We will start with our demo session. So sorry for the delay. Like I had received a wrong link, so that was the reason for the delay. So sorry for the delay. Okay. Yeah. And let me share my screen. Okay. So good afternoon, all. Today I'm going to give a demo on DFT. So DFT is designed for testability. DFT is designed for testability. So I'm going to give a demo session on DFT. So before we go into what is DFT, we will first try to understand what is VLSI. Okay, we will first try to understand what is VLSI. So VLSI stands for Very Large Scale Integration. Very Large Scale Integration. Okay, so that is what is VLSI. So it means implementation of millions of switches in a small area. So millions of switches is nothing but our MOSFETs. So millions of switches is the MOSFETs. So implementation of millions of switches in a small area. So that is what is called as VLSI. Coming to the motive of VLSI. So motive of VLSI means if suppose a company is designing a chip, so they will be having some primary conditions or primary targets that has to be met. That is what is the motive of VLSI. If any company is designing a chip, they will be having some primary conditions that has to be met. That is what is the motive of VLSI. So motive of VLSI is high performance. Next is low power. So we usually go for low power design in order to get longer battery life. In order to get longer battery life and then low area. So low area, why we go is if our chip size is less. If our chip size is less, then our product size will be less. Our product size will be less. So that is why we go for low area. Okay, if our chip size is less, then our product size will be less. So these are all the motive of VLSI. Like if any company is designing a chip, they will be having some primary conditions that has to be met. So one is high performance. Second one is low area. So low area, we need to go for low area because like if chip size is less, then product size will be less. And the other one is low power. So we will be going for low power design in order to get a longer battery life. Okay. And this is how our chip looks like. So as you can see in this picture in the right side. So after manufacturing, our chip looks in this way. Okay. So this is how our chip is. So now we have seen what is VLSI. So next we will see about ASIC. So ASIC stands for Application Specific Integrated Circuit. So that is what is the full form of ASIC. Application Specific Integrated Circuit. So that is the full form of ASIC. Okay. So if in case my screen sharing is not visible or if my voice is not audible, then you can unmute yourself and tell because while I'm presenting, the chat box will not be visible to me side by side. So after completing few slides, I'll just check that I will be checking the chat box. So if in case my screen sharing is stopped or like if I'm not audible, you can unmute yourself and tell. Okay. So yeah, we'll continue with that now. So ASIC stands for Application Specific Integrated Circuit. That is the full form of ASIC. So why it is application specific? It is because the chip, whatever we are designing, okay, the chip, the IC, whatever we are designing, it will be specific to a particular application. That is what is application specific integrated circuit. The chip, the IC, whatever we are designing, that will be specific to a particular application. So for example, if you are designing a chip for medical industry, then the chip can be used only in medical industry. It cannot be used in an automobile industry. Okay, so that is why. So application specific integrated circuit means the chip or IC, whatever we are designing, it will be specific to a particular application. Okay, so if you are designing a chip for medical industry, it can be used only in medical industry. It cannot be used in automobile industry. Okay, so that is what is application specific integrated circuit. Okay, so ASIC flow. ASIC flow means it actually gives the steps which we need to follow for designing a chip. So like ASIC flow means it actually gives the chip, it actually gives the steps which is involved in the process of chip design. So if if we are designing a chip, then it will be like we need to undergo all these steps. So that is what is ASIC flow. Okay. So ASIC flow means it actually gives the steps which we need to follow for designing a chip. Okay, so if we are going to design a chip, then we need to undergo all these steps. So what are all the steps which is involved in the chip design? That is what will be coming under ASIC flow. Okay, so the first step is the design specification step. Okay, the first step is the design specification step. So in design specification step, what will happen is, based on the application, based on the application for which we are designing the chip. Okay, so based on the application for which we are designing the chip. Okay, so certain factors will be decided, certain specifications will be decided, such as speed, like how many memory module, how many memory module memory module how many processors, how many processors, how many sensors, what is the power consumption, what is the power. So these kind of specifications will be decided during the design specification stage. Okay, so based on the application for which we are designing the chip, so certain factors like what has to be the speed, how many memory modules, how many processors, how many sensors, what is the power. So these kind of specifications will be decided during the design specification stage. So it will be decided by like experienced engineers. So they will be called as architects. So they will be deciding these kind of specifications. Okay. And after the design specification stage, we have the design code stage. So in the design code stage, the functionality of the design will be written in the design code stage. Okay, the functionality of the design of the chip, it will be written, and it will be written in Verilog or else in VHDL format. Okay, so this is what is the design code stage. Okay, so the design code of the chip will be written here. So it will be either in Verilog or else in VHDL. So it will be in behavioral model and data flow level model, behavioral model and data flow level model. Okay, so this is what will be happening during the design core stage. The functionality of the chip, that is the design of the chip, will be written. Okay, and it will be in Verilog or VHDL form. Okay, and after the design code stage, we have the verification stage. So verification stage, what do we do? What happens? So it is to validate the functionality of the design. So verification stage, it is to validate the functionality of the design, to ensure that, to ensure that, ensure that it meets the required specification, meets the required specification, and performs as intended, and performs as intended. Okay. So that is what is the verification. So verification team, what do? Is they validate the functionality of the design. So to ensure that it meets the required specification and performs as intended. So the design code, the functionality of the chip, it is actually written by the design team during the design code stage. So verification team, they actually validate the functionality of the design. Okay, so they validate the functionality of the design to ensure that it meets the required specifications and performs as intended. Okay. Now after that, we have the synthesis team. So synthesis team, what do? Is, so as of now, the design code, it is available in behavioral model behavioral model, and data flow level model. So synthesis team, what do they do is, this behavioral model and data flow level model code, it will be converted into a gate level netlist. It will be converted into a gate level netlist. Okay, so it will be converted to a technology node specific gate level netlist. Okay, or you can call it the same thing, technology node specific gate level netlist, or you can call it as a structural form or structural form. Both are same. You can call it as a structural form. Okay, so the behavioral and data flow level model code, it will be converted into a structural form. It is also called as technology node specific gate level netlist. So technology node means it is like 14 nanometer. So that is what is a technology node specific, 28, 14, okay, 28 nanometer, 14 nanometer. So these are all the technology nodes. Okay. So the behavioral and data flow level model code, it will be converted into a technology node specific gate level netlist. Okay, or you can even call that as a structural form. So that is what happens during synthesis team. Now after the synthesis team, we have the DFT team. Okay, after the synthesis team, we have the DFT team. So DFT team, what do? Is we insert some test structures in the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip, to help in the detection of manufacturing defects in the chip. Okay, so we will be inserting some test structures in the design during the pre-silicon stage, so which will help in the detection of manufacturing defects in the chip. So if suppose our chip fails after manufacturing, we will be able to tell what manufacturing defect has caused the chip to fail. Okay. So we will discuss about this design for test team much more in detail in our upcoming slides. Okay. And after that we have the PD team, physical design team. So physical design team, what do? Is they convert the gate level netlist into layout form. Convert the gate level netlist to layout form. So this is what will be done by the physical design team. They convert the gate level netlist into layout form. Okay. And after that, we have sign off. So sign off, three things will be done. One is STA, static timing analysis. Other one is physical verification, PV. Okay, physical verification. And then other one is LEC. LEC is logical equivalence checks. Okay. So STA as its name suggests, it is static timing analysis. Full form of STA is static timing analysis. So it is a method of validating the timing performance of the design by checking all possible paths for timing violations. So there will be various timing paths in our design. We will be checking whether there are any timing violations in those paths or not. That is what is STA, static timing analysis. So it is a method of validating the timing performance of a design by checking all possible paths for timing violations. And PV, physical verification, they actually verify the layout of the circuits. Okay, physical verification, they will actually verify the layout of the circuits. And finally, LEC. LEC is logical equivalence check. So in logical equivalence check, what do? Is we actually check whether the final form of the design which we are having, whether it is equivalent to the original design or not. Okay, so that is what will be checked during LEC. Okay, so why do we need to do LEC? Okay, so if you see chip design, it had started, the first step of chip design was the design code stage, where the behavioral and data flow level, where the design of the code, the functionality of the code was written. Okay, functionality of the chip was written, the design code of the chip was written, and it was in behavioral and data flow level form. Now during synthesis team, what has happened? This behavioral and data flow level format code, it got converted into technology node specific gate level netlist, or we even call it as a structural form. Okay. And if we go for low power design, then some more low power special cells, some special cells will be added, like isolation cells, clock gating, and then like retention registers, always on buffers, like that some special cells will be added. So those things also will be added during the synthesis time. And then design for testing, we will be adding our own structures into the design, like scan insertion, EDT insertion, MBIST insertion, like that we will be adding our own structures into the design. And then physical design time, what has happened, the gate level netlist has got converted into layout form. So if you see throughout the process of this chip design is undergoing a lot of changes. So that is why LEC is actually done in order to test whether the final form of the design which we are having, whether it is equivalent to the original design or not. Okay. So, sorry. That is what is LEC, logical equivalence checks. Sorry. Now after sign off, we have tape out. So tape out means it is to deliver the database to the manufacturing unit. So tape out means it is delivering the database, to the manufacturing unit. That is what is tape out. Okay, delivering database to the manufacturing unit. And finally, we have packaging and testing. So packaging means, so after manufacturing, this is how our chip looks like. Okay, so the big circle is the big circle which you see, that is called as a wafer, and each small portion will be called as a die. Okay, so packaging means protecting this die with a like covering this die with a protective layer. That is what is called as packaging. Okay, so covering this die with a protective layer, that is what is called as packaging. And testing means it is to test whether our chip is good or not, whether our chip is having any manufacturing defects or not. Okay, so that is what happens during packaging and testing. So packaging means, so this complete circle is called as a wafer and each individual portion is called as a die. So covering this die with a protective layer, that is what is called as packaging. And testing, it is to test whether our chip is good or bad, whether our chip has any manufacturing defects or not. Okay, so this packaging and testing, it is actually done after manufacturing. Okay, packaging and testing, it is done after manufacturing. Okay, so this is what is the ASIC flow. These are the various steps which is involved in the process of chip design. That is what is the ASIC flow. It actually gives the steps which is involved in the process of chip design. Okay, and in our later slides, in our upcoming slides, we will discuss more about this design for testing, DFT, and also about this testing. Okay, we will discuss in detail about the design for test and then this testing, much more in detail in our upcoming slides. Okay, so what is DFT? So DFT means it is to insert test structures in the design during the pre-silicon stage. So pre-silicon stage means before manufacturing. Pre-silicon stage means before manufacturing. Okay, to facilitate the detection of manufacturing defects in the chip. So to facilitate means to help in the detection of manufacturing defects in the chip. Okay, so if suppose a chip fails after manufacturing, okay, we will be able to tell what manufacturing defect has caused the chip to fail. What manufacturing defect has caused the chip to fail. Okay, so this is what is DFT. So DFT, we will be inserting some test structures in the design, like scan insertion, scan compression, MBIST insertion. Like that, we'll be adding some test structures in the design during the pre-silicon stage, that is before manufacturing, to facilitate the detection of manufacturing defects in the chip, to help in the detection of manufacturing defects in the chip. So if suppose a chip fails after manufacturing, we will be able to tell what manufacturing defect has caused the chip to fail. Okay. And now we will see what is the role of DFT engineer. Okay, what is the role of DFT engineer? We'll see. So DFT engineers, we will be adding some designs into the IC to make sure that testing is done properly. Okay, so as we saw in the previous slide. So DFT engineers, they do not check the functionality of the chip. We rather check the quality of the chip. Okay, DFT engineers, we do not check the functionality of the chip. We rather check the quality of the chip. So we'll try to understand this point with the help of an example. So here if you see in this figure, we are able to see a half adder. So this is an example. We'll try to understand this point with the help of an example. Okay. So here if you see in this design, we are having a half adder. Okay. In this picture, we are actually having a half adder. Okay. So we have seen one team, right, called as the functional verification team or else the verification team. Okay. So in the ASIC flow, after design code, we had a verification stage, right? So that will be done by the functional verification team. So what do functional verification team do and what do DFT team do? We will try to understand. So functional verification team, what do they check is, they will check if this half adder is functioning as intended or not. Okay, so this is the half adder. So functional verification team, what do they check? They will check, okay, whether the half adder is functioning as intended or not. Intended or not. So that is what will be checked by the functional verification team. So functional verification team, they will check whether the half adder is functioning as intended or not. DFT team, what do we do? DFT team, okay, DFT engineer, we do not check the functionality. What do? We check the quality of the chip. So which means we check whether each and every net of this half adder is free of defects or not. Is it free of defects or not? Okay, we will check whether each and every net of this half adder, whether it is free of defects or not. Okay, free of manufacturing defects or not. So we'll try to elaborate it. Okay, we'll try to understand this point. Okay, let me elaborate it slightly more. So for a half adder design, okay, for a half adder, what is the sum? Sum will be A XORed with B. Sum will be A XORed with B. And what is carry? Carry will be AB. Carry will be AB. So functional verification team, what do they do is, whether this is written correctly or not. That is what will be checked. Whether this is correct or not. Okay, whether this is correct or not. Correct or not. That is what will be validated by the functional verification team. So say for example, by mistake, if someone has written sum is equal to A or B. Okay, A plus B. Instead of XOR, they have given A or B, A plus B. Okay, and carry is equal to AB. Okay, sum is equal to A or B. So sum is equal to A or B. Instead of XOR, someone has written sum is equal to A or B and carry is equal to AB. So what will happen? This will not function like a half adder. Okay, this will not function like a half adder. This will not function like a half adder, because half adder sum should be A XOR with B, carry should be A. If someone has written sum is equal to A or B, carry is equal to AB, then this will not function like a half adder. So this is what will be checked by the functional verification team. So this is what will be checked by the functional verification team. Okay. So functional verification team. So that is, they are actually checking the functionality. Okay. So whatever design code has been written. Okay. So whatever design code has been written. Okay. Whatever design code has been written, whether it is functioning as intended or not. Okay, so that is what will be checked by the functional verification team. So whatever design code has been written by the design team, whether it is functioning as intended or not. Okay, so that is what will be checked by the functional verification team. So check the functionality. So for validate, okay, whether the design code written by the design team functions as intended or not. Functions as intended or not. Okay. So just a simple example I have taken here. Okay, just a very simple example I've taken here. So for half adder, if someone has written a sum is equal to A or B, then that will not function like a half adder, right? That circuit will not function like a half adder. So this is what will be validated by the functional verification team. So functional verification team, they validate whether the design code written by the design team functions as intended or not. Okay, so this is what will be checked by the functional verification team. Now, what is checked by the DFT team? So DFT team, okay, so DFT team, we do not check the functionality. DFT team, we do not check the functionality. Do not check the functionality. Okay, DFT team, we do not check the functionality. What do we check? We actually check whether each and every net of this half adder is free of manufacturing defects or not. Okay, DFT team, we check whether each and every net, each and every net of this half adder is free of manufacturing defects or not. Okay, so that is what will be done by the DFT engineers. So DFT engineers, we do not check the functionality, we actually check the quality of the chip. That is, we check whether each and every net, in this example, we will check whether in each and every net of the half adder, whether it is free of manufacturing defects or not. So say for example, this is our intended design. So you are having like A and then you are having B. So this will be coming from flops. So A XORed with B will give us sum. So this will be going to a flop. And A and B will be the carry. So this will be going to another flop. So this is the intended design. Okay, this is the intended design. So during manufacturing, okay, so during manufacturing, say for example, something has happened like this. So this is A, B. So this is sum. So each one is coming from a flop. Okay. And carry, it is coming here. And then this is B input. A input of this AND gate, say for example, it got unintentionally connected to ground. So the A input of this AND gate, unintentionally during manufacturing, A net of this AND gate got connected to ground. Okay. So say for example, during manufacturing, unintentionally, okay, A net of this AND gate, has got connected to ground. Okay. So these type of thing only will be checked by the DFT engineer. So we will be checking whether each and every net of this half adder is free of manufacturing defects or not. So this is only our intended design. So say for example, during manufacturing, the A net of this AND gate, it got unintentionally connected to ground. Okay, unintentionally it has happened. It's a manufacturing defect. So this is what will be checked, whether there are any manufacturing defects or not in our chip. That is what we will be checking. That is what the DFT engineers check. Okay, we will be checking whether our chip is free of manufacturing defects or not, whether each and every net of the design, whether it is free of manufacturing defects or not. Okay, whether each and every node and net of the design, whether it is free of manufacturing defects or not. So this is what will be checked by the DFT engineers. We do not check the functionality, we check the quality of the chip. So during manufacturing, unintentionally, if some net of the AND gate has got connected, this net of the AND gate, if it has unintentionally got connected to ground, so this is a manufacturing defects. So these kind of things will be checked by our DFT engineers. So we will check whether there are any manufacturing defects in our chip or not. Okay. And if suppose our chip fails after manufacturing, we will be able to tell what manufacturing defect has caused the chip to fail. Okay. So that is what is a DFT engineer. So now this testing, if you remember in the ASIC flow, we had done in the process of packaging and testing, right? So this was happening after manufacturing. So we were doing this after manufacturing. Okay. So after manufacturing, we were doing a process called as packaging and testing, right? So this is what is that testing. So 1 second. Just a second. Slide is actually missing. Just a second. 1 second. Just a second. Okay. So this testing is actually done after manufacturing. So in the process of after manufacturing, we have seen a process called as packaging and testing, right? So this testing is actually done there. Okay. So after manufacturing. So what is this testing? So testing is actually a process of determining whether a device is good or not. So in our case, it is a process of determining whether our chip is good or not, whether our chip has any manufacturing defects or not. So that is what is testing. Okay. So testing includes test pattern generation, application, and output evaluation. So this is what is testing. So first these test patterns will be generated. So these test patterns, it will be generated by the DFT engineers. These test patterns will be generated by the DFT engineers. So it will be done before manufacturing. Before manufacturing itself, we will be generating these test patterns. Okay. Before manufacturing itself, we will be generating all these test patterns. And these test patterns, it will be consisting of input sequence and expected output. These test patterns, it will be having the input sequence and expected output. Now, what do we do? So these test patterns, it will be applied to our chip. Okay, so this is only our chip. Our test patterns will be applied to our chip, and then the output of the chip, it will be compared with this expected output. Okay, the output of the chip, it will be compared with the expected output. So if the output of the chip, if it is equal to the expected output, then that means the chip is good. It is not having any manufacturing defect. Okay, if the output of the chip, if it is equal to the expected output, it means that the chip is good. It is not having any manufacturing defect. If the output of the chip, if it is not equal to the expected output, if it is not equal to the expected output, it means that there are some manufacturing defects in the chip. There are some manufacturing defects in the chip. Okay, it means that there are some manufacturing defects in the chip. So which means the chip has failed. It means that the chip has failed. Okay. So now after manufacturing, if a chip fails, okay. So after manufacturing, if a chip fails, so if a particular chip, if it fails on tester, okay. So after manufacturing, the chips will actually be tested on the tester, okay. So testing engineers, they cannot actually analyze it. DFT engineers will only analyze why that chip has failed. That is, DFT engineers will only be able to tell what manufacturing defect has caused the chip to fail. As I had told in the previous slide, right? So DFT engineers will only be able to tell what manufacturing defect has caused the chip to fail. Okay. So now possible outcomes of the testing. So what are all the possible outcomes of testing? We'll see here. So there are basically 4 possible outcomes of testing. So one is, if a good IC, if it passes the test. Good IC, if it passes the test means it is true pass. Okay, good IC means it has to pass the test. So if a good IC, if it passes the test means it is true pass. If a defective IC, if it fails the test, a defective IC, if it fails the test means it is true reject. Okay, defective IC, if it fails the test means it is true reject. Okay, defective IC means it should fail the test. So that is called as true reject. But if suppose a defective IC, if it passes the test, if a defective IC, if it passes the test, then that is called as test escape. It is also called as under testing. Okay, if a defective IC, if it passes the test, it is called as test escape. It is also called as under testing. Okay, and if a good IC, if it fails the test, good IC, if it fails the test, then that is called as yield loss. It is also called as over testing. Okay, good IC, if it fails the test, it is called as yield loss. It is also called as over testing. Okay, so goal of good testing. It will be to reduce this test escape and yield loss. Okay, goal of good testing will be to reduce this test escape and yield loss. So what is called as yield? Yield means number of good chips divided by total number of chips. So now out of a total number of chips which has been manufactured, how many chips are good? That is what is the yield. Okay, out of a total number of chips that has been manufactured, how many chips are good? How many chips do not have any manufacturing defect? How many chips are good? That is what is called as a yield. Number of good chips divided by total number of chips. Okay, so out of a total number of chips that has been manufactured, how many chips are good? Okay, so that is what is the yield. Now we will see what are manufacturing defects. So we have been telling in the previous slides that DFT engineers will be able to detect, we will be checking whether there are any manufacturing defects or not, and we will also be able to tell what manufacturing defect has caused the chip to fail. So we had been telling that in the previous slide. So we will see what are these manufacturing defects. Okay, so manufacturing defects means they are the defects that are caused by process variations and random imperfections. Okay, so manufacturing defects means they are the defects that are caused by random imperfections and process variations. So what is process variation? Process variation means slight variation in the transistor channel length, slight variation in the metal interconnect width and thickness. So all those things, it can actually impact in the logical and timing performance. So that is what is process variation. Random imperfection means, so it can result in unintended shorts, unintended opens. So those things are called as random imperfections. Okay, so the manufacturing defects are nothing but the defects that are caused by process variations and random imperfection. So process variation means slight variation in transistor channel length and slight variation in the metal interconnect width and thickness. So all those things, it will actually impact the logical and timing performance. So random imperfections means it can result in unintended shorts, unintended opens. So that is what is random imperfections. Okay. So in the next slide, we will try to understand what is the relationship between this defect, fault and error. Okay. So what is the relationship between defect, fault and error? So defect means it is the unintended physical difference between hardware implementation and its intended design. So if you consider, this is my intended design. Say for example, this is my intended design. I am having a 2-input AND gate. The inputs of these AND gates should be coming from flops, and then the output of the AND gate has to go back again to a flop. So this is my intended design. This is my intended design. Okay. So say for example, during manufacturing, we have seen, right, unintentional shorts, unintentional opens can happen. So that is what is a manufacturing defect. So say for example, this B net of the AND gate has got connected to ground. Okay. So this has happened unintentionally. Unintentionally. So according to the intended design, what has to come? B input of this AND gate, it should be coming from this flops output. But during manufacturing, what has happened? Unintentionally, B input of this AND gate has got connected to ground. That is what is a defect. Defect means unintended, okay, it is unintended physical difference between hardware implementation. So this is what is the hardware implementation. This is what is the hardware implementation, and this is what is the intended design. Okay, so that is what is a defect. Unintended physical difference between hardware implementation and its intended design. Okay, so that is what is a defect. Okay, unintended, it has happened unintentionally. Unintended physical difference between hardware implementation. So this is what is the hardware implementation, and this is the intended design. Okay, so this is the defect. And what is fault? Fault means logical abstraction or logical representation of the physical defect is called as faults. Okay, faults means logical representation of the physical defect. So in this case, the physical defect means we can call it as B input of AND gate has got connected to ground, has unintentionally got connected to ground, has unintentionally got connected to ground. This is what is the physical defect. The B input of the AND gate has unintentionally got connected to ground. Okay. So the logical representation of this will be, okay, if you want to represent this physical defect logically, we can say that B is stuck at 0. Okay, B is stuck at 0. Okay, B is stuck at 0. Okay, so that is what is the logical representation of the physical defect. So physical defect is nothing but B input of the AND gate has unintentionally got connected to ground. So logical representation of the physical defect will be called as the fault. So B is stuck at 0. B stuck at 0. So we can give like this. B stuck at 0. So that is what is the fault. Okay. And then error. Error means wrong output signal value. So due to the presence of defect or fault, if you are getting a wrong output signal value, that is what is called as an error. So say for example, this is our intended design. This is our intended design. Okay. So this is our intended design. So this is A, this is B, and then this is Y. So this is going here. This is flip-flop 1, this is flip-flop 2, this is flip-flop 3. And then this is during manufacturing. During manufacturing, unintentionally the B net of the AND gate has got connected to ground. So this is flip-flop 1, this is A. So this is flip-flop 2. So unintentionally the B net has got connected to ground during manufacturing. This has happened unintentionally. Okay. And this is the output Y. So this is going to flip-flop. Okay. So now error means it is wrong output signal value. So say for example, here if you apply 1-1 pattern in these two flops, if you write 1-1, what will happen? This A input and B input of the AND gate will also get 1. So the output of the AND gate will be 1. But the same thing here, during manufacturing, what has happened? The B net of the AND gate has got unintentionally connected to ground. So this flip-flop 1 and flip-flop 2, even if they have 1-1 value, 1-1 pattern is only applied. Okay, 1-1 pattern is only applied. But what is happening? A input, it is getting 1. But B input has unintentionally got connected to ground. B input has got unintentionally got connected to ground. So it will be 0. So 1 AND with 0 will be 0. So for this 1-1 pattern, if you see, we are getting wrong value at the output. We are getting wrong value at the output. That is what is called as error. Okay, wrong value, getting a wrong value at the output. Wrong output signal value is called as an error. So this is what is the relationship between defect, fault and error. Okay. So defect means it is unintended physical difference between hardware implementation and its, unintended physical difference between hardware implementation and its intended design. So that is what is a defect. Fault means logical representation of the physical defect is called as fault. And error means wrong output signal value is called as error. So in this case, if you see, for this 1-1 pattern, okay, for this 1-1 pattern, we are getting a wrong output signal value. We are getting 0. Okay, so it's a wrong output signal value. So this is what is the relationship between defect, fault and error. Okay. So let me just check the chat box once. Okay. So let me proceed. Okay. So next we will start with the flow of DFT. So flow of DFT, it is nothing but insertion. First is insertion. So that is addition of extra logic. So we will be adding some additional logic into our design, like scan insertion, EDT insertion, and then like MBIST insertion. Like that, we will be adding some extra logic into our design. So addition of extra logic is only called as insertion. Then generation. Generation is nothing but we will be generating the patterns. Okay, we will be generating the patterns. Okay, so the patterns will be having input sequence and then the expected output. These test patterns, it will be having input sequence and expected output. So if you remember these test patterns, whatever test patterns we are generating here, that will only be given to test the chip after manufacturing. Okay, that will only be used to test the chip after manufacturing. Okay, whatever patterns we are generating here, that will be given to test the chip after manufacturing. Okay, in the first like before some 3 or 4 slides back we have seen, right? And then validation. So validation means it is to check, so that during this generation step patterns are generated, right? Validation means it is to validate whether proper patterns are generated or not. Okay, validation means it is to check whether proper patterns have been generated or not. Okay, so why do we need to check whether proper patterns have been generated or not? Because patterns are generated by the tool only. Then why do we need to check if proper patterns are generated properly or not? So that is what is the need of simulation. We will discuss that in detail during our course syllabus. Okay. So this is what is simulation. So we'll be validating the patterns generated. So that is what is called as validation. So we'll be validating it by doing the simulations. Okay. So this is what is the flow of DFT. So first we have the insertion where we'll be adding the extra logic like scan insertion, EDT insertion, MBIST insertion, boundary scan insertion. Like that we will be adding the extra logic. Generation means we'll be generating the test patterns. And validation means it is to validate the patterns that are generated. Okay, so we'll be validating it with the help of simulations. Okay, so this is the flow of DFT. And now we'll just see what are all the course content, what are all the topics will be covered in our course, and we'll just give you a small overview on those course content. Okay, so this is our course outline. So first we will start with the scan insertion, then scan compression, which is nothing but the EDT insertion, then OCC, on-chip clock controller, OCC, ATPG, automatic test pattern generation, simulations, and then JTAG, joint test action group. Okay, and MBIST, memory built-in self-test, boundary scan. Okay, B scan or boundary scan. So these are all the course outline. Okay, all these are the course outline. So these are all the topics which will be covered in our syllabus. So now I'll just give you a overview of those topics. So what we will be discussing in these topics during our course, I'll just give you an overview of it in the demo session. Okay. So first coming to the scan insertion. So scan insertion means it is what will happen is all the normal flops in the design, they will be converted to scan flops. And these scan flops, it will be stitched into a scan chain. Okay, all the normal flops, they will be converted into scan flops, and these scan flops, they will be stitched into a scan chain. Okay, so this is what is scan insertion. So what is the functionality of a scan flop? So what is the functionality of the scan chain? All those things we will discuss it in detail during our original course. Okay. So as of now, I'm just telling the definition of scan insertion alone. So all the normal flop in the design, it will be converted to scan flops, and these scan flops, it will be stitched into a scan chain. Okay. So the functionality of scan flop, the functionality of scan chain, all those things we will discuss it during our course syllabus. Okay. And now we will see what is the need of scan insertion. So need of scan insertion is, it is to gain controllability and observability of the design. Okay, need of scan insertion means it is to gain controllability and observability of the design. That is, to easily control and observe our design, we will be going for scan insertion. Okay, so that is what is the need of scan insertion. In order to easily control and observe our design, we will be going for scan insertion. Okay, so in order to understand that point, let's take an example. So what does it mean, like in order to easily control and observe our circuit? In order to understand that point, let's take an example. Okay, so this is an example. So I'm having a design. Okay, so which is a 10-bit counter. I'm having a counter initialization circuit and then a counter observation circuit. So suppose that the counter is failing. Okay, suppose the counter is failing. That is, after counting 999, instead of counting 1000, it is again counting 999. So that is the reason why the counter is failing. Okay, so I'm having a design in which there is a 10-bit counter, a counter initialization circuit is there, and then a counter observation circuit is there. So suppose that my counter is failing. That is, after counting 999, instead of counting 1000, it is again counting 999. Okay, after 999, counter has to count 1000, right? But instead of counting 1000, it is again counting 999. So that is the reason why the counter is failing. We're just assuming, okay? We're just taking an example. So, how many clock pulses are required by the functional verification team and DFT team to find out that the counter is failing? We'll just try to see now. How many clock pulses are required by the functional verification team and DFT team to find out that the counter is failing? Okay. So, functional verification team, as we saw earlier, they will be checking the functionality. Functional verification team, they actually check the functionality. So in our case, counter where it is failing? Counter is failing at the 1000th pulse. Counter is failing at the 1000th pulse. Okay, so the counter is actually failing at the 1000th pulse. So at the 1000th pulse only, instead of counting 1000, it is again counting 999. So for this, counter has to count for 1000 pulses. Still 1000 pulses, the counter has to count. So for this, 1000 pulses will be required for this itself. And then few more pulses will be required. Some more pulses, few more pulses for counter initialization and counter observation. Few more pulses will be required for counter initialization. That is, in order to bring the counter to the initial state, and counter observation. The output of the counter, it has to be taken to some register and the register has to be read. So for that, few more pulses will be required. So all the above, we can tell that functional verification team, they require more than 1000 clock pulses to detect that the counter is failing. More than 1000 clock pulses they require. The same thing if you see for DFT engineers, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. That is, it can be somewhere around 80 or 90 or 150, like that, in the range of 100 clock cycles. Functional verification team, they require more than 1000 clock pulses. DFT team, we require in the range of 100 clock pulses to tell that the counter is failing. Somewhere around 80, 90, 150, like that. So you can see the difference, right? The difference is in the clock pulses. So DFT engineers, we are able to tell that the counter is failing in very much less number of clock cycles. So functional verification team, they require more than 1000 clock pulses. DFT team, we just require in the range of 100 clock pulses to tell that the counter is failing. Okay. So how we are able to tell this in such less number of clock cycles? So for that, you need to understand what is a scan cell, how does a scan cell function, okay? And then we need to also you also need to understand the scan chain operation, so which will be covered in our course. So during the course, we will tell how DFT engineers, we are able to tell that the counter is failing in very much less number of clock cycles. Okay, during the course, we will tell that. Okay, so we are able to tell this in less number of clock cycles because we are easily able to control and observe our circuit. Okay, as a result, so how we are able to easily control and observe our circuit? It is because we have gone for scan insertion. That is what is the need of scan insertion, to gain controllability and observability of our design. In order to easily control and observe our design, we will be going for scan insertion. Okay. And additionally, DFT engineers will be able to tell what manufacturing defect has caused the counter to fail. Okay, as I had been telling in the previous slides, DFT engineers, we will be able to tell what manufacturing defect has caused the chip to fail. So in this case, what manufacturing defect has caused the counter to fail, we will be able to tell that. Okay. So this is what is a scan insertion. So during the scan insertion topic, so these are all the subtopics which will be covered in our course syllabus. So that is first, what is a scan cell, and then what is a scan chain, scan cell and scan chain. Then DRCs and scan insertion will be covered. And then edge mixing and domain mixing topics, scan chain balancing. So those things will be covered, edge mixing, domain mixing. So that is coming under a scan chain balancing topic. And then we'll give you an overview of scan chain reorder. Scan chain reorder. So scan chain reorder will be actually done by the physical design team. So we will just give you an overview of scan chain reorder, and also some more short definition type things will be covered, like what are all the types of scan cells. So such kind of small definition type things will be covered. Benefits of scan insertion. So some short theoretical topics will be covered in the like scan insertion topic. Okay, so these are all the major topics, that is scan chain, scan cell, DRCs, edge mixing, domain mixing, and then scan chain reorder, overview of scan chain reorder. So these are all the major topics which will be covered. Apart from that, some small definitions also will be covered. Okay, small definition type theoretical topics will be covered during scan insertion topic. Okay, and next is scan compression. So scan compression means a single scan channel is internally divided into multiple scan chains. So if you see in this diagram, a single scan channel, it is internally divided into multiple scan chains. That is what is called a scan compression. Or else you can tell that these internal chains, they are compressed into external channels. These internal chains, they are compressed into external channels. You can tell in both ways. So these are the internal chains. These are the internal chains. These are the external channels. These are the external channels. Okay. So you can tell like a scan channel is internally divided into multiple scan chains. Like that also you can tell. Or else you can tell that internal chains, they are compressed into channels. Internal chains, they are compressed into channels. Like that also you can tell. Both are correct only. And why do we need to do this? Why do we need to compress the internal chains into channels? Why do we have to do that? Okay, why do we have to compress the internal chains into channels? Why do we need to do that? It is actually done in order to reduce the test time. In order to reduce the test time, and also in order to reduce the test data volume. So test data volume is nothing but the number of bits of patterns. Number of bits of patterns. That is what is the test data volume. Okay. So need of scan compression is in order to reduce the test time and in order to reduce the test data volume. Test data volume is nothing but number of bits of patterns. Okay. So if you are using Mentor Graphics Descent tool, okay, if you are using the Mentor Graphics tool, then for achieving the scan compression, we will be adding one logic called as EDT. So for achieving compression, we will be adding a logic called as EDT. So the full form of EDT is embedded deterministic test. Embedded deterministic test. Okay, embedded deterministic test. What is the full form of EDT? Okay, full form of EDT is embedded deterministic test. So if you are using Mentor Graphics tool, in order to achieve the scan compression, we will be adding one logic called as EDT. So the full form of EDT is embedded deterministic test. So during our course, what we will be covering is, we'll just be covering what is scan compression. Okay, what is scan compression we will be covering. And then we will also cover like how scan compression will be is actually reducing the test time and it's actually reducing the test data volume. So how it is done? So with the help of logically, as well as with the help of formula, we will show you how scan compression is able to reduce the test time and reduce the test data volume. So we will show you that. And also this EDT logic. So the structure and the components of EDT logic. So in EDT, we will be having 4 components. One is the decompressor, other one is compressor, other one is controller, and the last one is the bypass logic. So these are all the components of the EDT logic. Okay, all these are the components of the EDT logic. So we will discuss about each and every component. So what is a decompressor? What is the structure of a decompressor? What role it plays in scan compression? Same way for compactor, same way controller, same way bypass logic. So each and every component in the EDT logic, we will be covering it in our course syllabus. Its structure and what is its need, like what role it plays in the process of scan compression. So that is what will be those things will be covered during scan compression topic. Okay, and then next one is automatic test pattern generation. Next one is the automatic test pattern generation. Okay, which is nothing but ATPG. So what is ATPG? As its name suggests, okay, automatic test pattern generation. As its name suggests, it is actually a process of generating test patterns for a given fault model. So there will be various fault models which we will be discussing, like stuck at fault model, transition delay fault model, path delay fault model, IDDQ fault model. Like that, there are various fault models which we'll be discussing. So ATPG stands for automatic test pattern generation. So as its name suggests, okay, automatic test pattern generation, as its name suggests, it is used for generating test patterns. It is used for generating test patterns, or it is a process. It is a process of generating test patterns for a given fault model. Okay, it is a process of generating test patterns for a given fault model. So during ATPG, test patterns will be generated. So as its name suggests, okay, ATPG, automatic test pattern generation. So it is a process of generating test patterns, right, for a given fault model. So during ATPG, test patterns will be generated. So after manufacturing, if suppose there are any defects, then these test patterns should have the capability to detect most of the manufacturing defects. So after manufacturing, if there are any manufacturing defects in our chip, means our test patterns should have the capability to detect most of the manufacturing defects. Okay. So how does a tool able to generate this kind of a test pattern? How does a tool is able to generate a test pattern which is having this capability? So how the tool is able to generate is, during ATPG, what our tool tries to check is, it will check if a particular defect occurs after manufacturing, will it get detected or not. So by doing the tool during ATPG time, what it will do is, it tries to check if a particular defect occurs after manufacturing. Okay, if suppose a particular defect occurs after manufacturing, will it get detected or not. So that is what will be checked during ATPG time. Okay, so now you might get a doubt. So ATPG process, it is actually we are doing it before manufacturing only. ATPG process, we are doing it before manufacturing only. So how does our tool know before manufacturing itself whether a particular manufacturing defect will get detected or not? So how does our tool know that? Because at the time of ATPG, we are still there in the before manufacturing phase. So before manufacturing only, we are like generating this test pattern. So how does our tool know before manufacturing itself whether a particular manufacturing defect will get detected or not? Okay, so that is because our tool, it does a process called as fault simulation. It does the process called as fault simulation while it is generating the test patterns. Okay, so what is fault simulation? What is fault simulation? Okay, so this is only the process of fault simulation. So at the time of ATPG, we will be giving our design to the tool. Okay, during ATPG, we will actually be giving our design to the tool. So what does the tool do? The tool, it will keep this design. The tool, it will actually keep this design. The tool will keep this design, and in its internal memory, it will create another copy of this design. In its internal memory, it will create another copy of this design. Now, in this created copy of this design, what the tool will do is, it will induce all the faults into it. It will induce all faults into it. Okay. So fault means it is a logical representation of physical defect, as we saw in the earlier slide. Fault means it is a logical representation of physical defect. Okay. So the tool will induce all the faults into it. So by doing this, what is the tool trying to do? By doing this, okay, what are all the the tool, what it will do is, what are all the possible manufacturing defects that might occur, everything the tool will induce it into the design. Okay, what are all the possible manufacturing defects that might occur? Okay, everything the tool will induce it into that design. That is what is called as, it will induce all faults into it. Induce all faults into it means, what are all the possible manufacturing defects that might occur, everything the tool will induce it into this design. Okay, everything the tool will induce it into this design. Okay, so by doing this, what is the tool trying to do? The tool okay, the tool is just trying to mimic all possible failure situations, mimic all possible failure situations, okay, failure situations that might occur after manufacturing. That might occur after manufacturing. Okay, so what is the tool trying to do? Okay, by doing this, what is the tool trying to do here? What are all the possible manufacturing defects that might occur? Everything the tool will induce it into the design, into the created copy of the design. So why it is called as fault? Fault is nothing but logical representation of physical defect. So that is why it is called as a fault list. By doing this, the tool is just trying to mimic all possible failure situations that might occur after manufacturing. Okay, the tool is just trying to mimic all possible failure situations that might occur after manufacturing. Okay, and this design where the tool has induced all the faults, right? So that design is called as the faulty machine. And then the design which we have given, it is called as the good machine. The design which we have given, it is called as the good machine. Then what the tool will do? The tool will apply patterns. Okay, the tool will be applying pattern for the good machine. Okay, so the tool will apply patterns. The tool will apply patterns, input sequence for the good machine. And then the output of the good machine, it is called as the expected value, or we can even call it as the good value. Then what the tool will do, the tool will apply patterns for this faulty machine, and then the output of the faulty machine, we will call it as the faulty value. Then what the tool will do, the tool will compare this good value and then the faulty value. The tool will compare this good value and faulty value. So if good value and faulty value, if both are mismatch means if both are different. If good value and faulty value, if both are different, then the tool will tell that if suppose this defect occurs, if suppose this fault occurs after manufacturing, it will get detected with a test pattern. So that is why it will place the faults into the detected class. So say for example, we'll just consider, so good value is 1, faulty value is 0. So good value and faulty value, they are mismatch. Mismatch means they are different. Okay. So good value good value, it is not equal to the faulty value. Okay. So what will happen? So what does it imply? So for a particular fault, for a particular pattern, okay, for a particular fault, if a particular pattern, if it gives good machine simulation as 1 and faulty machine simulation as 0, what does it imply? It implies that if suppose this defect occurs after manufacturing, if suppose this defect occurs after manufacturing, then the response of the chip, along with the defect, will be 0. Okay, will be 0. Okay, and expected value will be 1. That is what it implies. Expected value will be 1. Okay, so if suppose this defect occurs after manufacturing, then the response of the chip along with the defect will be 0 and then the expected value will be 1. So what will happen if it is like this? We will be able to see that there is some problem with the chip. Okay, so we will be able to see that there is some problem in the chip. We will be able to see that there is some problem in the chip. Okay, so this defect, if suppose it occurs after manufacturing, if suppose it occurs after manufacturing, it will get detected with this test pattern. Okay, that is what it implies. It will get detected with this test pattern. Okay, so what is the tool? What will the tool do? So the tool has created a, so the tool is having a good machine. The tool is having a good machine and it has created a faulty machine. The tool is applying input for good machine and the output of the good machine is the good value. Then the tool has applied patterns input for the faulty machine and the output of the faulty machine will be the faulty value. Then what the tool is doing? The tool is comparing the good value and the faulty value. So if good value and faulty value, if both are different. So say for example, I have taken one example. Good value is 1, faulty machine simulation is 0. So what does it imply? It implies that, okay, so for a particular pattern, for a particular fault, okay, for a particular pattern, for a particular fault, good machine simulation, it is giving 1, faulty machine simulation, it is giving 0. So if it is like this, what does it imply? It implies that if suppose this defect occurs after manufacturing, then the response of the chip along with the defect will be 0 and the expected value will be 1. So we will be able to see that there is some problem in the chip. So if suppose this defect occurs after manufacturing, it will get detected with that particular test pattern. And hence the tool will place that fault into the detected class and it will write that pattern into the pattern list. Okay, it will write the pattern into the pattern list and it will place the fault into the detected class. So detected class means, so the faults, so any of the faults in the detected class, if suppose it occurs after, it will get detected with a generated test pattern. That is what is called as detected faults. Okay, so if suppose fault from that class occurs after manufacturing, it will get detected with a generated test pattern. Okay. And then say for example, now the tool is doing the comparison, right? So good value and faulty value it is comparing. So good value and faulty value is no mismatch. No mismatch means if both are same. No mismatch means if both are same. What will happen? Okay. So say for example, good value is equal to 1. Good machine simulation for a particular fault, for a particular pattern gives good machine simulation as 1 and faulty machine simulation as also 1. So same, this same. So what does it imply? It implies that, okay, if suppose this defect occurs after manufacturing, it will not get detected. Okay, it will not get detected. So what does it imply? So like for a particular fault, if a particular pattern gives good value is equal to 1 and faulty machine simulation value is also 1. So what does it imply? It implies that if suppose this defect occurs after manufacturing, then the response of the chip along with the defect will be 1 and expected value is also 1. So we will not be able to see that there is some problem in the chip. So if suppose this defect occurs after manufacturing, it will not get detected. That is what it implies. Okay. So if suppose, what does it imply? It implies that if suppose this defect occurs after manufacturing, it will not get detected. So hence the tool will place it into the not detected class. Okay, good value, good machine simulation and faulty machine simulation, if they are same, the tool will place it into the not detected class. Place those faults into the not detected class. So not detected or undetected class, which implies that not detected or undetected class means it implies that if suppose any of the faults from this class occurs after manufacturing, it will not get detected with a generated test pattern. Okay, so this is how the tool is able to generate test patterns which is having the capability to detect most of the manufacturing defects. So if suppose there are any manufacturing defects, our test pattern will be able to detect most of the manufacturing defects. So how is the tool able to generate such kind of a test pattern? The tool is able to do it because it is doing a process called as fault simulation for generating the test pattern. So in the time of fault simulation, what is the tool trying to do? The tool is just trying to mimic all possible failure situations that might occur after manufacturing, and it is just trying to see what will be the response. So it is just trying to find a pattern that will be able to detect the fault if suppose it occurs after manufacturing. Okay. So this is how the tool is able to generate a test pattern which is having the capability to detect most of the manufacturing defect if suppose it occurs after manufacturing. Okay. So during ATPG, there are no actual failures. What is the tool trying to do? There are no actual failures. What is the tool trying to do? The tool is just trying to mimic all possible failure situations that might occur after manufacturing, and it tries to find a pattern to detect that failure situation, okay. So if suppose it occurs after manufacturing, okay. So during ATPG there are no actual failures. The tool is just trying to mimic all possible failure situations that might occur after manufacturing, and it tries to find a pattern to detect that failure situation if suppose it occurs after manufacturing. So these patterns are only written into the pattern list. Okay, these patterns are written into the pattern list. Okay, and these test patterns, so whatever test patterns, so these test patterns only will be given to test the chip after manufacturing. So if you see in this slide, in the previous slide, during the testing slide, if you see, so in the previous slide here we have seen, right, So we have written right DFT engineers before manufacturing will be generating the test pattern. So with the help of ATPG only we will be generating these test patterns. So these test patterns, whatever has been generated during ATPG, that will only be used to test the chip after manufacturing. And these test patterns, what capability they have? So if suppose there are any manufacturing defects, our test patterns will be having the capability to detect most of them. So how the tool is able to generate test patterns with such kind of a capability? It is because the tool is doing fault simulation and it is generating the test pattern. And what happens during fault simulation? What happens during fault simulation? The tool will just try to mimic all possible failure situations that might occur after manufacturing, and then it tries to find a pattern that will be able to detect that failure situation if suppose it occurs after manufacturing. And this pattern only it will flight it into the pattern list. And this is how the tool is able to find out, generate a pattern list which is capable of detecting most of the manufacturing defects. Okay. So fault is nothing but logical representation of manufacturing defect. So manufacturing defect is nothing but physical defect. Fault is nothing but logical representation of the manufacturing defect. Okay, so here the tool is inducing the fault. We call it as tool is inducing the fault. It is nothing but it is we call it fault here because it is logical representation of the physical defect. Okay, physical defect we call it as a defect. Logical representation of the physical defect we call it as a fault. Okay. So manufacturing defect. So there is no terminology called as manufacturing faults. So manufacturing defects. Fault means it is a logical representation of manufacturing defects or physical defects. Okay. So yeah, okay. So ATPG is actually a very vast topic. So we will be covering this fault simulation once again in detail during ATPG, and also we will be like with the help of few examples also we will cover this fault simulation, and then we will see some topics like fault classes, then fault categories, then fault models, that is stuck at, transition delay, path delay, and then IDDQ. So these fault models we will be covering. And in ATPG labs, we will be doing about the coverage analysis and coverage improvement. Okay. So coverage analysis means what it is. So after doing fault simulation, the tool will classify the faults into various classes like detected class, not detected class, like that it will classify. Detected class means what does it imply? It implies that if suppose any of the faults in this class occurs after manufacturing, it will get detected with a generated test pattern. That is what is detected class, detected faults. Undetected or not detected faults means what does it imply? It implies that if suppose any of the faults in this class occurs after manufacturing, it will not get detected with the generated test pattern. That is what is not detected fault. Okay, if suppose any of the patterns from this class occurs after manufacturing, it will not get detected with the generated test patterns. So that is what is undetected faults or not detected fault class. So coverage analysis means what we have to do is we have to see why the tool was not able to find a pattern in order to detect those faults if suppose it occurs after manufacturing. So that is what is analysis. We need to analyze and we have to see why the tool was not able to find a pattern that will be able to detect that fault if suppose it occurs after manufacturing. That is what is coverage analysis. And then coverage improvement. Coverage improvement means we have to do something. We have to do something, okay, like test point insertion, like that we have to do something in order to make those faults also to be detected if suppose it occurs after manufacturing. Okay, we have to do something so that the tool will be able to find a pattern that will be able to detect those faults if suppose it occurs after manufacturing. Okay, so that is what is coverage improvement. So coverage analysis and coverage improvement we will discuss it in our lab session. We'll be doing it in the lab sessions. Okay, so this is what is ATPG. Okay, ATPG is a vast topic, so it will like many topics will be covered in that. Okay, during our original course. And next one is the simulation. So simulations, it is actually to validate the patterns that are generated during ATPG time. So we have seen right at the time of ATPG, the tool was generating test pattern. So in order to check whether proper patterns are generated or not. So the patterns which are generated during ATPG, so those patterns only it will be used to test the chip after manufacturing. So before we use the test patterns to test the chip after manufacturing, we will validate whether the test patterns which was generated is proper or not. Okay. So that is done by the process called as simulation. And why do we need to check whether proper patterns was generated or not during ATPG time? That is what is the need of simulation. So that we will cover it during our original course. Okay. So simulation means it is to validate the patterns that was generated during ATPG. So at the time of ATPG, we are generating test patterns. So these test patterns only will be given to test the chip after manufacturing. So before we use the test patterns, before we give the test patterns to test the chip after manufacturing, we will validate once whether the test patterns are generated, whatever test patterns was generated, whether it is proper or not. So that is what will be done by the process called as simulation. So what is the need of simulation? Why we need to do the validation? We will discuss it during our course, during the simulation topic. So simulation is also done before manufacturing only. Okay, simulation is also done before manufacturing. Okay. And next one is the JTAG. So JTAG is Joint Test Action Group. Okay, Joint Test Action Group. So it's a IEEE 1149.1 standard. Okay. So the need of JTAG, why DFT engineers we use JTAG is in order to minimize the number of ports from top level and also to achieve boundary scan. Okay, in order to minimize the number of ports from top level and in order to achieve boundary scan, we will be using JTAG. So we will try to understand these 2 points. Okay. So minimizing the number of ports from top level. So here if you see, I have kept a list of some important DFT signals. Okay, here I have kept a list of some important DFT signals. So in order to control all these signals, okay, these are some important signals alone. So there will be many more signals like this. Okay, these are some list of important signals alone. There will be many more signals like this. So if all these signals are to be controlled from the top level, that is if we allocate a top level port to control MBIST PG enable, one top level port to control BIST setup, one top level port to control memory bypass enable, one top level port to control EDT bypass enable, then for the Intel test enable, XTEL test enable, into mode, X mode, like that for each and everything. If we allocate a top level port, okay, if we allocate a top level port to control each and every signal, then what will happen? Number of top level ports will increase drastically. Number of top level ports will increase drastically. Okay. So if we allocate a top level port in order to control each and every signal, then what will happen? The number of top level ports, it will increase drastically. So that is why only we will be using JTAG. Okay, we will be using JTAG to internally control the static signals. Internally control the static signals. So we'll be using JTAG to internally control the static signals. So static signals means they are the signals that do not change the value throughout the run. Okay, so that is what is a static signal. Static signal means they are the signals that do not change their value throughout the run. Okay, that is what is static signals. So in order to internally control the static signals, we will be making use of JTAG. So with the help of JTAG, we are internally controlling the static signals. So as a result, we are able to minimize the number of ports from the top level. Okay, now with the help of JTAG, what we are doing, we are internally controlling the static signals. So as these static signals are internally controlled using JTAG, the number of ports from the top level, it can be minimized. Okay, so that is how JTAG is actually used to minimize the number of ports from top level. So in the JTAG course, we will be discussing about the JTAG TAP architecture. Okay, the JTAG FSM, the various states of JTAG FSM. We will also take an example illustration and we'll just explain the various states of JTAG FSM. And by explaining that, we will also simultaneously see how with the help of JTAG, we are able to internally control those static signals. Okay, we will see that. Okay. So this is one need of JTAG. And the other need of JTAG is to achieve boundary scan. So how with the help of JTAG you are able to achieve boundary scan? For that you will be, you need to know the JTAG architecture. So that we will cover it during our course. As of now, we will see what is boundary scan. Okay, as of now, we will just see what is boundary scan. Okay. So chip 1, chip 2, chip 3, they are passing the test of DFT, but still the board is failing. Chip 1, chip 2, chip 3, they are passing the test of DFT, but still the board is failing. So what can be the reason? Okay. So what does it mean is, so first the chips will be manufactured. First the chips will be manufactured, and after that what will happen? The chips will be tested on tester. Chips will be tested on tester. So ATE. Chips will be tested on tester. That is on ATE. So already we have seen in the starting slides, we have seen, right, at the process of testing. Okay, manufacturing. After manufacturing, we are done packaging and testing, right? So that is what the chips will be tested on the tester. Okay, tester is nothing but ATE, automatic test equipment. Okay, so the chips will be tested on ATE. So you can imagine it like this. So this will be the ATE. So this will be the ATE. Here we will be testing the chips. So here in our example, we are having 3 chips. Chip 1, chip 2, chip 3. So the input of the chip will be coming from ATE. The output of the chip will be going back again to the ATE. So like this, it will be there. Okay, so the chips are actually tested on the tester. That is on ATE, it is tested. So in this example, what is happening? Okay, in this example, chip 1, chip 2, chip 3, they have passed their test on ATE. Okay, chip 1, chip 2, chip 3, they have passed their test on ATE. They have passed their test on ATE. Okay, so if they have passed their test on ATE, what does it mean? It means that they are not having any manufacturing defects. They are not having any manufacturing defects. They are not having any manufacturing defects. So chip 1, chip 2, chip 3, they have passed their test on the tester, that is on ATE, which implies that there are this chip 1, chip 2 and chip 3, they are not having any manufacturing defects. Now once the chips are tested on the tester, what will happen is these chips, it will be placed on the board. These chips will be placed on the board. Board is nothing but the PCB board. It will be placed. So this chip 1, chip 2, chip 3, they will be placed on the board, and then these interconnections and all will be formed. Okay, so these interconnections and all will be formed. Okay. So now what is happening? The board is being tested. Now after this, board is tested, and when the board is being tested, board is failing. When the board is being tested, the board is failing. So what can be the reason why the board is failing? So chip 1, chip 2, chip 3, they are not having any manufacturing defects because they have already passed their test on ATE. So chip 1, chip 2, chip 3, chip 1, chip 2, chip 3, they have already passed their test on ATE. So it implies that they are not having any manufacturing defects. Just a second. So chip 1, So chip 1, chip 2, chip 3, they are not having any manufacturing defects. So chip 1, chip 2, chip 3, they are not having any manufacturing defect, that we are sure. Now when the chips are placed on the board and when the board is being tested, it is failing. So why it is failing? It is because there can be some problem, manufacturing defects in the interconnection between the chips. So there are some interconnections are formed between the chips, right? So there can be some problem in the interconnection between the chips. So that is why the chips are failing. That is why the board is failing. So the problem, it can be problem. So like there can be some manufacturing defects in the interconnection between the chips. So that is why the board is failing. Okay, just a second. So there can be some manufacturing defects in the interconnection between the two chips. That is why the board is failing. There can be some manufacturing defects manufacturing defects in the interconnections, between the two chips, okay. So that is why the board is failing. Okay, there can be some manufacturing defects in the interconnection between the two chips. So that is why the board is failing. Okay. So why do we use boundary scan? We use boundary scan in order to test the interconnection between the two chips. In order to test the interconnections between the two chips, we will be going for boundary scan. Okay, in order to test the interconnections between the two chips only, we will be going for boundary scan. Okay, so we will discuss in detail during our boundary scan syllabus. We will discuss like the structure of boundary scan cell and how with the help of JTAG we are actually able to do this boundary scan, and also some instructions like sample preload, X test, bypass. So those instructions we will be discussing it during our course. Okay. So this was regarding the boundary scan. And MBIST, as its name suggests, its name is memory built-in self-test, MBIST. So MBIST, as its name suggests, it is memory built-in self-test. So memories, they are actually a combination of analog and digital components. So we will be having separate MBIST technique in order to test the memories. Okay. So memories, it is a full form of MBIST test, memory built-in self-test. So memories here actually a combination of analog and digital components. So we will be using separate MBIST techniques in order to test the memories. So in the MBIST course, what are all the things we will be covering is, we will be covering the memory fault models. We'll be covering the memory fault models. Then some algorithms which will be able to detect those faults. Okay, how it will be able to detect those faults. And then we will be covering the Tessent MBIST. So how MBIST is implemented in Tessent. So Tessent MBIST implementation, Tessent MBIST architecture, Tessent MBIST operation protocol. So all those things, grouping of memories, so step concept. So all those things we will be covering it during our MBIST course. Okay. And also practicals of MBIST also we will be covering MBIST insertion, pattern generation, and then simulation, MBIST pattern simulation also we will be covering. Okay. And if suppose simulation fails, MBIST pattern simulation, if it fails, how to debug that. So all those things we will be covering it during our MBIST topic. Okay. So also we will also be, during this MBIST topic, we will also be covering IEEE 1687 standard IJTAG. Okay, 1687 standard, it is called as the IJTAG. So in order to understand Tessent MBIST, you need to understand IEEE 1687 standard IJTAG. So we will be covering that as well. IEEE 1687 standard IJTAG also will be covering. I have not kept it in the demo session because in order to understand IJTAG, you need to understand what is JTAG first. So that is why I have not kept it in the demo session, but we will be covering it in our original course. Okay. So apart from this, we will also be covering OCC, on-chip clock controller. Okay, on-chip clock controller, OCC, that will also be covered in our syllabus. Like what is the structure of OCC, what is the need of OCC, where do we place the OCC, placement of OCC. Okay, how to decide how many OCCs are required, where to place the OCC. So these kind of things will be covered during our course syllabus. Okay. So in labs, we will be doing the IJTAG insertion, MBIST insertion, scan insertion. There are actually two approaches in scan insertion. One will be the top-down approach and the other one will be the hierarchical approach. So we will cover both these scan insertion, both these approaches we will cover. EDT and OCC insertion, ATPG pattern generation, ATPG and MBIST simulations. So all those things we will be covering it in our lab sessions. Okay, so these are all the topics which we'll be covering in the lab session. So for boundary scan, we will not be covering the practicals because we do not have the license for boundary scan. Okay, boundary scan practicals is not covered because we do not have the license for boundary scan. And simulations, we will be covering only the no timing simulation. Simulation, we will be covering only the no timing simulation, because for timing simulation, in order to do timing simulation, we require a file called as SDF file, standard delay format. One file is required in order to do the timing simulation. So that file is not available in our institute. So that is why we will be doing only the no timing simulations. Okay. And then boundary scan also we will be covering only theoretically. We will not be doing the practicals of boundary scan because we do not have that license. Okay. So these are all the concepts which will be covered in the lab. So JTAG insertion, MBIST insertion, scan insertion. So there are two approaches. One is top down, other one is bottom up. That is nothing but hierarchical scan. EDT OCC insertion, ATPG, and MBIS simulations. So we will be doing only no timing simulations. Okay. So that's it. And our labs, it is actually four levels. Okay. In our labs, we are actually having four levels. Okay. Level 1, level 2, level 3, level 4. Okay, our labs are divided into four levels: level 1, level 2, level 3, level 4. So in level 1 projects, we are totally having 11 test cases. So these are like small test cases, like complexity will be less. So maximum of around 100 flops will be there. Okay, maximum of 100 flops like that it will be there. Okay, so for these 11 test cases, we are going to perform the scan insertion. Then in level 2 projects, for the same 11 test cases, we are going to do the EDT insertion, ATPG and simulations. So this is what we will be covering it in our level 2 project. Level 3 projects, it is hierarchical approach, hierarchical scan approach. Okay. So these are like test cases with higher complexity. So for level 3 projects, you will be having around 4K flops. So in level 3 projects, we'll be doing the complete flow, that is JTAG, then MBIST, then EDT OCC, scan, ATPG, simulations. So everything we will be doing it in our level 3 projects. So it's a bottom up approach. So around 4K flops will be there. Complexity is high. So around 4K flops will be there. So JTAG, MBIST, OCC, all those insertion and all will be doing it here. So the level 1 and 2 projects, we are just doing scan insertion, EDT, ATPG and simulation. So in level 3 and level 4 projects, we'll be doing completely JTAG insertion, MBIST insertion, EDT, OCC insertion, scan, ATPG, everything we'll be doing. Okay. And level 4 projects, it is a top-down approach. Level 4 projects is a top-down approach. So here you will be having around 44K flops. Around 44K flops are there in level 4 projects. Again, the same thing. Whatever you have said, right? Everything will be doing it. So JTAG, MBIST, EDT, OCC, scan, ATPG simulations, everything will be doing it. Okay. So this is how our labs are structured. Okay. So level 3 and level 4 projects, they are labs with higher complexity. So you can, while writing in your resume, you can mention level 3 and level 4 as your project work. Okay, DFT project work. So tools used for DFT. So these are the various tools which is available for DFT in the like market. So what we will be using is, we will be using the metagraphics tools. Okay. So for MBIST insertion, we will be using Tessent MBIST. For scan insertion, we will be using Tessent Scan. For scan compression, we will be using Tessent Test Compress. ATPG also we will be using Tessent Test Compress. Simulation, we will be using QuestaSim. Okay, simulation will be using QuestaSim. And in one step, we need to do synthesis. So for doing synthesis alone, we will be using the synopsis tool, which is design compiler. Okay, which is the design compiler. Okay. So all the other tools are metagraphics. Only synthesis we'll be using the synopsis tool, which is the design compiler. Rest of the other things, rest of all the DFT related things, we will be making use of the metagraphics tool. Okay. MBIST is Tessent MBIST, scan is Tessent Scan, compression is Tessent Test Compress, ATPG also Tessent Test Compress, simulations Questa Simulator. Okay, Questa Sim. So we'll be using the metagraphics tools. And that's it. Who and all can attend the course? So like if you are a student from final year semester, okay, if you want if you have DFT in your course curriculum, you can attend this course. Or else like final semester, if you're a final semester student, if you want to join VLSI field, okay, join VLSI field as a DFT engineer, you can attend this course. Okay. Any new college graduate. So any new college graduate, if you want to join the VLSI domain and you want to take up the DFT as a DFT engineer, if you want to join the VLSI domain, so you can also take up this course. So from relevant branches of engineering like EC, E&I, so you can all take up this course. Okay. So new college graduate, if you want to join the VLSI domain, okay, as a DFT engineer. And then lecturers or professors who want to switch their career into real-time industry experience. So if you are like a professor in VLSI field, now if you want to move on to industry, so you can also attend this course. And then working professional from similar or other VLSI domain. So say for example, you are a functional verification engineer or you are a physical design engineer. Now you want to change your domain to DFT. So in that case, you can attend this course. Okay. Or say for example, you are working in IT. Now you want to switch to VLSI. So in that case, you can also attend that course. Okay. So if you are there in the VLSI domain itself, some other domain like physical design or DV, if you're there in some other domain, if you want to switch to DFT, you can attend this course. And if you're working in some IT field and if you want to like, say for example, you're working in some IT field, you want to switch to VLSI as a DFT engineer, you can also attend this course. So placement support, we are having tie-up with various VLSI companies. So like during the course, you will be like given various course assignments, tests will be conducted, mock interviews will be conducted. Okay, so all these things will be there, mock interviews will be conducted. So based on your performance in these assignments, mock interviews, these tests, presentation sessions, so based on your performance in all these activities, you will be added to a group called as job support group. So in the job support group only, the VLSI placement opportunities will be posted. Okay. And we will also train you with previous company interview questions and answers. We will train you like what are all the previous company, what are all the interview questions were asked. So all those things we will give you the training. Okay. Previous company interview questions, what are all the things which were asked, and we will also teach you the how to answer those questions also we will teach you. Okay. Yeah. And that's it with my demo. So do you have any doubts, any queries to ask? You can ask me. Do you have any doubts or any queries?
Hello, ma'am.
Yes, Chaitanya.
Yeah, studied in relevant engineering course only, like ECE, and I have worked on another domain, like digital marketing. So now I want to switch into this DFT engineer. This course is eligible for me.
Yes, you will be. This course will be eligible for.
Okay.
Okay. You can also once confirm it in your individual group. So there will be an individual group which is created with your VLSIGuru ID and your VLSIGuru name. Once you get enrolled in the institute, so you'll be having one individual group with your name and your VLSIGuru ID. You can just post this query there, and you can once get their confirmation as well before starting the course.
Okay. Okay.
So does anybody have any doubts related to the course content and syllabus? For simulations, we have VCS license, but we will be covering the QuestaSim tool. In the course syllabus, we will be covering with the QuestaSim tool. So like, if you want to learn like VCS tool, you can like message in your individual group. So if possible, they will arrange those sessions as well. Okay, VCS tool is there. But in the course syllabus, we will be using the Questa Sim tool only for simulations. So if you want to use it and if you want any guidance, you can message in your individual group. So one individual group will be created. So you can message them. You will be getting support. So if possible, like they will give you support and they will also train you with the VCS tool as well. Coding knowledge, it is not very compulsory as far as DFT is concerned. So you need to have an idea about tickle scripting. Okay, so tickle scripting will be covered in the course syllabus itself. So during the first few months, you'll be having the basics training where you'll be covering digital design, then CMOS, Verilog, Linux. So at that time, this tickle scripting will be covered in the course syllabus itself. Okay, so tickle scripting, you need to have some knowledge. And then Verilog you can have Verilog you can have some knowledge. Okay, so small knowledge on Verilog you can have. Okay. So DFT, it will be like considered as it will be coming both in the front end domain as well as in the back end domain. So front end means all the process which is there before synthesis, that we usually call it as a front end, and back end means all the processes after synthesis, we will be calling it as the back end. So DFT, we will be doing some insertions like MBES, TDT, OCC insertion, all those things we will be doing it in the front, like before synthesis we will be doing it. So and after synthesis also, like scan insertions, those things also we'll be doing, and then those ATPG simulations, all those things also will be done after synthesis. Okay, so DFT can be considered as both in front end as well as in back end. Okay, it will be like DFT will come as a part of both front end and back end. Okay, so like usually what we do is um, so this is synthesis, right? So this is synthesis. Okay, so before synthesis, before synthesis, we will be doing before synthesis we usually call it as front end, and after synthesis we after synthesis we call it as the back end. Okay, so before synthesis we call it as a front end, after synthesis we call it as a back end. So in DFT we will be doing a process in both these things. We'll be doing process in both the things, like in before synthesis also we will be doing certain insertions like MBEST insertion, EDT OCC insertion, those things we'll be doing it before synthesis as well. After synthesis also we'll be doing those scan insertions, and then those ATPG simulations, all those things it will be happening after synthesis as well. So you can consider that DFT, it will come as a part of both front end and back end. Okay. Yes, DFT engineers, yeah, as I told, like front end DFT will be coming as a part of both front end and back end. Okay, so before synthesis, we usually call it as front end. After synthesis, we usually call it as back end. So, like before synthesis, also we are having some tasks. After synthesis, also we have some tasks. So that is why you can consider DFT as both front end and back end. Okay. Course duration. So course duration will be totally, the course duration will be 5 months, where first 2 months will be basics training. Basics training. So which will be like digital design, then Verilog, Tickle, CMOS, all these things will be covered. Linux, all those things will be covered. And then the next 3 months training will be DFT, where all the topics, whatever I have given in the course outline, the scan insertion, scan compression, ATPG simulation, JTAG boundary scan, all those things will be covered during these 3 months. Okay. So total duration of the course will be 5 months. Usually the course will be for 5 months. Okay, it might sometimes get extended, like this basic training, it can get extended to, instead of 2, it will be like 2.5 months. Same way, this DFT training, it can be some 3 to 3.15 months, it can get extended. So usually the course will be for like 5 months, but sometimes if it gets extended, then you will be, your course will be for 6 months. Okay. So like you can also like, there will be one individual group which is created there, and you can also check there about the course duration. Okay. They will also give you the schedule for the course as well. They will also, if you request it, they will also give you the schedule for the course. Okay. So usually it will be around 5 to 5.5 months. So yes, for online pre-recorded sessions will be there. Yes. So like, yeah, recording, the live class recording also will be there. Pre-recorded session means like e-learning trainings will also be there. Okay. So course timings, it will actually differ from one batch to the other batch. So I'm not very sure about the course timing. But before course, right, like before like once you enroll into the course, so the schedules will be posted in your groups. Okay, groups will be created, DFT groups will be created for your batch. So in that batch, the schedule will actually be posted. The timings will actually be posted. Okay. So the timing is actually differing from one batch to the other batch. So that is why I'm not really very sure about the timings. Okay. So you can like message in, you can like message in the individual group, same individual group. One group will be created with your VLSIGuru ID and name. You can message there, so you will get like idea about the timings as well. Theory and labs, yeah, that is what like in each batch it is actually different. So it depends on that. So what is happening is, so some batches we will be having theory. Okay, theory. This is during the weekend. So theory in the morning we are having, theory in the morning we will have, and then labs in the afternoon. Labs in the afternoon we will have it. Weekdays will be lab practice. Weekdays will be lab practice. So in this lab, we will be explaining the test cases. During this lab practice, you will be opening the tool and you'll be practicing it. Okay, so during weekdays, lab practice session will be there. Okay, this was like this for some, for a few batches it was like this. For some batches, weekend we have theory in the morning, theory in the morning. Okay, so this usually it will be around 10 to 1. This will be 3 to 5. This will be 10 to 1. Okay, so same way. Theory it will be around 10 to 1 a.m. And then weekdays, any 2 days, any 2 days, we have labs. We have labs from 7 p.m. to 9 p.m. Okay, we had labs for 7 p.m. to 9 p.m. Like any 2 days, like Tuesday and Thursday, like that, the labs will be having. Okay, 7 p.m. to 9 p.m. And then we will also, weekdays, we will also be having lab practice session um, during the weekdays. So from 10 to 1, you will be having the lab practice session. Or else in another batch, how it is there is weekend we are having theory, theory plus lab. We are having theory is 10 a.m. to 1 p.m. Lab is 3 to 5. So we are having it like this. Okay. So and then again during the weekdays also, we will be having lab session from 10 to 1. So this is for 2 days we will have it. And next 2 days we will be having the lab practice. Lab practice. So 10 to 1 it will be like this. Okay. So this lab will be for weekend students. This lab will be for weekend students. This lab is for weekday students. Weekday students. So like that for each batch, the course duration, the course schedule and then the timings are varying. Okay, so for your batch, what is the course timing and how the course schedule will be there? It will be posted in your DFT group, okay, by the management. If you want to know now, then one individual group will be created for you. So you can post it in that group and you can get the schedule and timings for your batches, for your particular batch. Okay. Practicals for online mode, we will be doing the labs and showing you. At that time, you will be taking some notes like that. You will be doing those things. Okay, so during the lab sessions. Okay, so during these lab sessions, so lab sessions will be conducted both for online as well as offline students. This lab session will be conducted. So where we will be doing the labs and you will be taking some notes and you'll just be watching the session. And during the lab practice, again, this is for both online as well as offline. Lab practice will be there. So you will be practicing it. And then if you encounter any errors or if you are having any doubts or if you're stuck anywhere, you can let us know. So we will take access of your VNC and we will try to solve your errors. Yes, we have classes on Saturdays and Sundays. All Sundays we will be having classes. So do you have any other questions? Demo session recording, it will not be available in the platform. So demo session recording, demo session, you can request in your individual group. They will take they will just give you a YouTube link. Okay, so in the portal, all the regular session classes will be available. Demo sessions class, it will not be available in the portal. It will be if you request in your individual group, they will give you the YouTube session link. Okay, so the YouTube link they will actually give. Okay. Demo session alone, it is like that. All the rest of the other sessions, recordings, you can get it from the portal. Okay, you can get it from the portal. So I'll just attach the exact answer for DFT coming under front end or back end. I've just posted it in the chat box. So you can just see that. You can just read it. So DFT comes under both the front end and back end. So definition of front end flow is responsible to determine a solution to a problem and transform it into RTL description. So in DFT, like MBIS, DDT, OCC insertion, all those things we'll be doing it there. And definition of backend flow is it is responsible for physical implementation of a circuit. It transforms RTL description into physical design composed of gates and interconnections. Okay. So in DFT, after MBIS and DDT OCC insertion, we actually synthesize a design. Scan insertion is performed on the gate level netlist. Okay, gate level netlist. So that is what is like DFT. We can consider that it comes under both front end as well as back end. Okay. So career gap, whether it will affect in placements, can you discuss this with Srinivasa sir? So sir will be having more experience on this. So sir will be able to give you good guidance on that. Do you have any other doubts? Okay. So if you get any other doubts, right? So once you enroll into the institute, one individual group will be created. So where with your VLSIGuru ID and VLSIGuru name, one group will be created. So in that group, you can post any doubts, whether it is related to technical doubts or any tool related doubts or any fees related doubts, schedule related doubts, whatever doubts you have, placement related doubts, whatever doubts you have, you can post it in that individual group and you will get those doubts clarified. Yes, placement assistance will be given. So we will be like training you with previous company interview questions. We will also train, like we will be training you how to answer those questions. We will take previous company interview questions and we will teach you like how to answer those questions. We'll be teaching you. We will be giving you mock interviews so that you will get an idea about the original what is it interview environment. Okay, one mock interviews also will be conducted, and then you will, in order to improve your communication skills, like those what is it those presentation sessions, all those things will also be conducted. Okay, so based on your performance in all the test communication, sorry, presentation session, mock interviews, and then we will also be providing you some assignments during the course. So based on your performance in all these things, we will be adding you to a group called as job support group. So in that job support group, you will be having placements. The placement opportunities will be posted. So recently some of them are getting placed in DFT domain. So if you want to get a clear picture on it, you can like discuss it with Srinivasa sir. So regarding the how the market is there and how the DFT jobs are there. So those things you can like discuss it with Srinivasa sir. So sir will be in a good position to guide you on that. So as far as my opinion is concerned, so the DFT job openings, it will be less, but at the same time, number of students who are applying for the job position will also be less. Okay, number of students who are applying for the job position will also be less. So there is a chance that you will get selected in the there is like higher chance that you will get selected in the interviews. Okay, because in say for example in DFT you're having around 20 students means, and say for example in physical design and all you're having 70 students means, the number of students who are applying for that position will be less in DFT. So there is a higher chance that you can get selected in DFT domain. But these placement kind of, this is just my opinion. Okay, so these kind of placement kind of questions you can market, how the market is there, and regarding those placement kind of questions you can like discuss it with Srinivasa sir. So sir will be in a good position to guide you on those things. So any other questions do you have? Okay, so there are not any more questions, like we can end today's demo session. If you get any questions, you can post it in your individual group. You will get clarification on your doubts. Okay, so whether it is technical or placement related doubts or anything, schedule, timings, fees, tool related doubts, anything if you have, you can post it in your individual group. So your doubts will get clarified. So yeah, thank you all. We will end today's class.